Okay, good morning, everyone. So my name is John Guan from North University. Currently, I'm a postdoc over there. From this August, I will be joining the State University of New York at Buffalo as a temporary assistant professor. Today, I'm going to talk about WNOS, called an optimization-based wireless network operating system. This work is in collaboration with my colleagues Lorenzo Batizola over there, Emily John Lemiers, and also Professor Martin Malodier. So first, the objective. What do we want to do in our research? So yeah, at a high level, what do we want to do in our research is to explore new approaches to control complex wireless networks. So why? Think that we are entering the era of Internet of Things. Tens of billions of devices will be connected to the Internet, which will create a very complex wireless networks. So the question is, how to control the complex networks? What's the best way to control the future complex networks? What is the problem? Let's say what's the limitations with today's wireless networks. Basically, today's wireless networks have been based on inflexible architectures. It's based on hardware-based. It's very hard to adopt new technologies. For example, if you want to implement a new technology, basically you need to redesign a new chip or reprogram the FPGA. Some of us have been working on programming FPGA. We know that the learning curve is kind of pretty steep because it involves some kind of hardware level programming. So as a result, the innovation in wireless networking has been significantly hindered. So how about software-defined radios? Can we design complex wireless networks using software-defined radios, for example, USRP, lookup devices, and so on? Yes, we can, but it's still very challenging. Why? Think about that. We have a CPU. We want to design a complex software. What do we need? We need a computer architecture. We need an operating system to abstract the computing resources, to abstract the storage resources, right? So this a software-defined radio device, just like a CPU without the computing architecture, without the operating system. So how can we design a complex wireless network without all of this? Right? So you may ask, okay, can we just reuse the architecture of the existing wireless networks? That's what we have. First, the traditional network architecture, which is a layered architecture. We have from the physical layer up to the application layer. One layer is built upon the lower layers, but different protocols have been defined at the different layers. Actually, the layered architecture has been the key of the success of the Internet in the past decades. But it's not a good abstraction for wireless networks. Why? Because wireless networks, by the way, in this research, we focus on the wireless ad hoc networks. The wireless control is very complicated because it's on one hand vertically coupled among the different protocol layers. On the other hand, it's horizontally coupled among different nodes where they mutual interference. So how about software-defined networking? SDN has been proposed to simplify the management of networks. The core idea is to separate the data plane and the control plane. And they implemented the control plane in a centralized manner. Because of this architecture, it usually requires a high-speed front haul to collect global network information. So it's not the best approach to control wireless networks. So basically, what we are doing in today's wireless networks is to write very complex cross-layer control programs manually, which is very hard to adopt new technologies. As a result, the gap between the theoretical research and also the practice of wireless networking is growing bigger and bigger. So basically, in our research, we are trying to do to bridge the gap between the software-defined networking and also the distributed network control, and hence to bridge the gap between the theoretical research and also the practice of wireless networking. That's why we want to study the basic design principles of wireless network operating system, or WNOS for short. Okay, that's what our objective. So let's see what exactly is WNOS? What do we do with WNOS? Basically, WNOS is, we have a network here. WNOS is over there. So basically, WNOS provides an abstraction of the wireless network, which is a set of APIs based on which The users, the network operators, can define different network control objective programs. For example, maximize throughput, minimize delay, minimize energy consumption, different control objectives. These control objectives can be defined in a centralized manner using high-level programming languages. For the user-defined centralized control program, WNOS will decompose the centralized program into a set of distributed control programs, and for each of the in an automated manner. For each of the resulting distributed programs, a numerical solution algorithm will be generated again in an automated manner to solve the problem to optimize the parameters of a programmable protocol stack, which is installed at the distributed network devices to drive the distributed devices to interact with each other based on the local network information to achieve the user-defined network social network control objective. It's the high level of idea of WNOS. Okay, next let's take a closer look at the network abstraction. So I just mentioned the objective of the abstraction is to provide an interface based on which the users can define network control objectives. With the defined program, a mathematical model, which is a centralized mathematical model, will be constructed automatically and then decomposed. This is not easy at all. There are several challenges to be addressed. But because first, the wireless network is very dynamic, it's dynamic wireless channels with joining and leaving network nodes. Also, what is even worse is that the challenge comes from the heterogeneous network behaviors. Just to give you a sense what it is, what it means. For example, in wireless network, a node may behave a source of a session, a flow, a relay, a destination, the interferer or the neighbor, or behave as the class head. So a single node, the same node, behave in very different ways. So it makes the abstraction of wireless networks really challenging. To address this challenge, in WNOS, we proposed a three-layer abstraction architecture: the control interface, network representation, and also mathematical model. Here, I'd like to focus on the representation. Basically, wireless network can be represented like this. The network devices are characterized into one. A is represents the primitive device elements. B represents the virtual elements, and also I represents the relationship between the different elements. Let's say what is a primitive element? Basically, I want to go to the details of the definition, but when we say a primitive element, we refer to a single network element. For example, a single node, a single link, or single session. It's a single network device. But when we say a virtual element, we refer to a set of network devices. It's not a single one, but a set of devices, like a set of neighbor nodes, a set of active links, or set of sessions. So it's different from primitive. And a set of relationships have been defined to characterize the relationships between the primitive elements, between the virtual elements, and also between the primitive and the virtual elements. For example, here we have a node. A node has a set of neighbor nodes as an attribute of the node. And in a set of neighbor nodes, each member is a node. So we define different relationships to characterize the wireless network, basically based on a directed multigraph. This is how we design the network representation. Just some high-level idea here. So with the user-defined centralized control problem, WNOS will decompose the centralized program into distributed ones in an automated manner. This is not easy, because so far there's no existing tools that can be used to perform automated decomposition. In our research, we designed the automated decomposition based on available decomposition theories. First, let's take a look at the decomposition framework. First, the decomposition follows two steps: the vertical decomposition and also the horizontal decomposition. By the way, here we want to clarify that our objective is not to propose any new decomposition series. Instead, our objective is to design the automatic decomposition based on available decomposition series, and our resulting framework is not limited to any specific decomposition series. Okay, the first step, the vertical decomposition, is the objective is to decouple the coupling among the protocol layers. So, for example, based on some decomposition series, for example, the dual decomposition, we have a mathematical expression of the problem. By introducing the Lagrange coefficient, we can obtain a dual expression of the problem. Then by decomposing the dual expression, we can decompose the original problem. Some of us have been working on this area, are familiar with the framework of layering as optimization decomposition. The output of this step is a set of subproblems, each involving only a single protocol layer. And each of the problems will be further decomposed horizontally. For example, the core idea of the horizontal decomposition is to let each network agent to optimize a modified version of the original utility function. For example, here, this is the original utility function. So we define a modified version of the utility function for each distributed individual node, which is a function of the original utility function plus a penalization. If we define the penalization like this, we have the simplest case, which is the best response. Otherwise, if we define the penalization like this, we can achieve the distributed gradient algorithm or the decomposition by partial linearization, which is the most recent theoretical research about the decomposition. Here, the penalization, the intuition of the penalization is that to prevent a node to hurt the network too much, hurt the other user too much. If it's hurting the other too much, it will be penalized more. So some of us have been working on cross-layer design, distributed network control. You may ask, okay, we have known this decomposition series. So what is new here? What is a challenge here? So actually, the challenge is in the automated decomposition. We want to perform the decomposition in an automated manner, not manually. So let's say what exactly is the challenge. Basically, the main challenge comes from the fact that the virtual network elements can't be determined not until at the network runtime. So remember, what is virtual network elements? So when we say a virtual network element, we refer to a set of network devices, for example, a set of neighbors, nodes, a set of sessions, and so on. This virtual elements can't be determined until at the network runtime. So basically, mathematical centralized network control problem that may involve a set of virtual elements, for example, the set of sessions, set of links, and so on. They are not known until network runtime. So it means that when we design WNOS, when we want to design the decomposition rules, we don't have a specific network control problem. So how to perform the decomposition without even knowing the problems? It's a challenge. So what can we do? You may have guessed, okay. We propose to decompose via the instantiation. The high-level idea like that. With a user-defined centralized control problem with a set of virtual elements, we first create an instance of the abstract problem by creating an instance for each of the virtual elements. Then we decompose the resulting instance of the problem, then apply the resulting decomposition rules at network runtime, which can be arbitrary network control problem. So the question is, how to generate instances? Can we generate the instances arbitrarily? No. Because we want the resulting decomposition rules can be applied to arbitrary network control problems at the network runtime. So the question is, can we design a set of special instances so that the resulting decomposition rules can be applied to arbitrary network control problems at the network runtime? To answer this question, we proposed an approach called disciplined instantiation. The core idea is to impose a set of rules in the generation of the instances of the virtual elements. The first rule is called equality. What does it mean? It means when we generate the instance for the virtual elements, the resulting instances for the same type of virtual elements must have the same cardinality or the same number of members. We'll have more details about here. Give an example. The second rule is called ordered uniqueness. Because during the decomposition, the members of an instance may be reordered. So we need the instance to be mapped, even after being reordered, we need the instance to be mapped to the right, the unique virtual element. Now that we have an example here. We have four nodes A, B, C, and D. We need to create an instance for each of the four nodes A, B, C. Create, for example, the neighbors, the set of neighbor nodes. The first rule says that the instance is created by pure random sampling. It means that by selecting randomly a subset of members from a larger set. The first rule says all the instances must have the same number of elements. So we can say that it's not good for instance A and D. The rule A will be validated. Why? Because instance A has 5 members, but instance D has only 4 elements. Why it's not good? Because during instantiation, if we have such a set, we don't know if we should map it back to the virtual element of the neighbor set of A or for D. We don't know. It's confusing. The second rule is guaranteed by hash checking, which is first sorting the virtual elements, then create a unique ID by using hash functions. We can see that the instance A for A prime and C prime is not good. The rule 2 will be violated. Why? Because after reordering the elements, the two instances will result in the same hash ID. So basically, the rationale for the two rules is to guarantee a one-to-one mapping between the virtual elements and the instances. So we can apply the decomposition rules to the arbitrary network elements, arbitrary network control problems at network runtime. So let's have a core example. First, here we consider a specific network control problem involving two protocol layers, physical layer and the transport layer. The objective is to find the optimal transmission powers for all the links at the transport physical layer, and also the optimal transmission rate at the transport layer to optimize the network-wide utility function, which can be defined as the sum utility or sum rate or sum log utility. Here we can say that there are a set of virtual elements. For example, the set of sessions, the set of active links, and also the set of links used by each session. We have different virtual elements to be instantiated to decompose in an automated manner. First, we create an instance for the two global virtual elements. For example, we use 4 active links and also 3 active sessions. Then let's see how we create the instance for the local virtual elements. We create an instance for the set of links used by each session. We create an instance. For example, session 1 uses links 1 and 2, session 2 uses 2, 3, and session 3 uses 2, 3, links 3 and 4. We can see that all the instances for the local virtual elements, the same type of virtual elements, have the same length and they have the same unique ID. So it means the two rules can be guaranteed. As a result, we can create an instance of the network with 3 sessions and 4 links. For the session 1 uses links 1 and 2. Then we can obtain a specific network control problem. With the very specific mathematical expression. Then we can, for example, if we consider the dual decomposition, we can introduce the Lagrange coefficient. Then we can decompose it vertically to decouple the coupling between the physical layer and the transport layer. This is the result of the vertical decomposition. Of course, the subproblem at the physical layer can be further decomposed horizontally into distributed subproblems. Here, let's take a look at the transport layer subproblem. We have 2 coefficients, lambda 2 and lambda 3, which are the Lagrange coefficients. What does it mean? How can we use the decomposition result at network runtime, mapped to the general decomposition rules? So how to determine the signaling coefficient? Basically, if you take a look at the generation of the instances, you can find that the combination of 2 and 3 is namely the set of links used by each session. So it means that at network runtime, a session only needs to collect coefficients from all the links along the path used by the session. Then how to generate the signaling automatically. So basically here, I want to put the details here. So basically, with given decomposition series, we convert the resulting mathematical expression to the symbolic domain. So basically, we enable automatic signal generation based on symbolic computing. This is the idea of how to enable automatic problem decomposition. So basically, for each of the resulting sub-problems, a numerical solution algorithm will be also generated automatically to optimize the parameters of a programmable protocol stack. Right? So far, this sounds good. So you may ask, does it work? We have built a test bed based on software-defined radio devices, which has 21 USFPs, to test the idea. Basically, the prototype follows a 3-tier architecture. At the top tier, first tier is a WNOS control host. Most of the WNOS components are implemented here, including the abstraction, instantiation, and also the automated decomposition. Let's take a look at how it works. Here we have an example of the APIs abstraction provided by WNOS. If it's the abstraction APIs, you can specify the network type. You can specify the protocols used at the different layers. You can define the utility function, define constraints, and also you can specify the decomposition approach series to be used. With the user-defined program, the mathematical model will be constructed automatically, and the solution algorithm will be generated automatically to optimize the programmable protocol stack. We have developed a protocol stack spanning from the physical layer to the abstraction layer with different optimization parameters at the different layers. For example, at the physical layer, we can optimize the transmission power and also the channel coding rate. We can optimize the window size of the TCP protocol at the transport layer, for example. This is a snapshot of the test bed. We test the distributed control programs automatically generated by comparing it to schemes, for example, the grid control schemes, and also the schemes without cross-layer control. We can see that significant utility gain can be achieved here in different cases. But you may ask, okay, we have been working on cross-layer, okay, design distributed control. We can do even better, more easily in many different other ways. So why it matters? So I want to say that the utility gain here with WNOS, you can achieve the gain by writing only several lines of code. By defining the centralized control problem using high-level programming languages, you don't have to be the expert of the distributed network optimization. You don't have to be the expert of the protocol design. You don't have to master software-defined radios. Right? Can we do something else? Yeah. If we want to change the network behaviors, for example, we can define the control objective to maximize the sum rate of the network. We can to minimize the power of the network. We can see that very different network behaviors can be achieved. For example, with rate maximization, here we have two flows. If we stop one flow, the one flow is down, the other flow will go up to maximize the sum rate. But if the objective is to minimize the power, after one flow is finished, the other flow will maintain the rate because the objective is to minimize the power, not maximize the rate. So here, what do we want to see that the different network behaviors can be achieved by modifying only several lines of code, very convenient. the distributed control programs will be generated automatically. Another advantage benefit of WNOS is that we can conveniently deploy a large-scale network. For example, here we have a network of 21 USRPs, 21 nodes, with source nodes, destination nodes, and also relays, different network rules. By generating programs for different network nodes, we only need to write a single piece of code. Then the distributed control programs will be generated automatically for different nodes. So it means that it's the benefits of WNOS. It's the flexibility and the scalability of WNOS. Of course, so far there are a lot of work about software-defined networking, about software-defined wireless networks. For example, the Open Radio software one, and also CLFD. I won't go to the details of the related work of each of the approach. Here, I would like to highlight that the novelty of the work of WNOS that based on WNOS, you can define the control objective in a centralized manner, while the distributed control programs will be generated automatically based on rigorous distributed optimization series. It's the whole idea of WNOS. Of course, there are a lot of open challenges. First, in the current design of the WNOS, in the abstraction, the mathematical models of the wireless networks need to be explicitly specified. Can we design an approach to come up the mathematical models in an automated manner? Also, the current design of WNOS has been based on deterministic optimization. So next step, maybe it's interesting to study statistic optimization. Also, security issues hasn't been studied. And also, next step, we will standardize the interface so we can integrate the new software-defined network framework with other IPM frameworks, for example, the OpenFlow, the WNOS, and so on. Okay, this is the logo of the project, and there's a link of the project where you can find all the source code of the WNOS. With WNOS, we provide a new way to design and control the future wireless networks. Thanks.